Bismillahirrahmanirrahim. Assalamu alaikum. Hello and welcome to lecture number 23 of Algebraic Topology. So far we have done the definition of homology and some tools. In today's lecture we are going to learn some more tools to calculate homology, and we will apply them and see how to calculate the homology. For example, we will see how to calculate homology of a torus, and in our previous discussion we have already calculated the homology of a torus. But then we will see in today's lecture that using these tools how simple it is to calculate the homology of a torus as compared to our previous calculations. So let's begin with today's lecture. So we have this definition of retract, and we will apply this definition and calculate the homology. So we need it in our today's discussion. So retract. So consider a space X and a subspace A of X. Okay, the subspace A is called retract if the inclusion map I from A to X has left inverse. Okay, so of course, if A is subspace of X, then we can define the inclusion map A to X. Okay, so this is just the identity map, but the domain is restricted to A. Okay, so for example, consider I from R1 to R2. Okay, so R1 is a one-dimensional real vector space contained in this two-dimensional real vector space. So I can define this embedding in the following way. So every real number goes to R0. So what is this embedding? So basically we have R2 as a plane, and I'm taking this R, I'm identifying this R with this x-axis. Okay, so in other words we can say that this R1 is subspace of R2. Okay, so that's what this embedding map means. Okay, so we are taking elements of A and we are identifying them as elements of X. Okay, so we have this map and it has left inverse. So left inverse means that the following condition holds. Okay, so R composition I is basically identity of A. In other words, we can say that we have A to A as the identity map, identity of A, and this A is embedded into the space X, so this is the I map, and we have this map R. Okay, and this expression means that this diagram is commutative. So in other words, if we start from A, go to X, and then from X to A, it is the same as going from A to A using the identity map. Okay, so that's what it means by a retract. Now, what is deformation retract? So a subspace A of topological space X is called deformation retract if the inclusion map has left inverse such that this is homotopic to the identity of X. Okay, so the condition retract comes with the condition that R composition I is equal to the identity of A. So this is already included in the definition of deformation retract. Moreover, this map, so first apply R on X and then go to A, and then embed this A into X, then this map is basically homotopic to the identity of X. Now let's see what does this definition mean. So let's consider this to be a space X and this to be a space X, and let's say this is the identity map. Okay, so the identity map will take elements of X to the elements of X. So what about this I composition R? So R takes elements of X to the elements of A. So R takes these elements to some subset A of X. Okay, so this is R of X. Okay, now when we apply this I map on the image of X under R, then basically we are realizing the elements of R of X as elements of X. So remember that I is a map from A to X and R is a map from X to A. Okay, so when you define this map from X to A, and this is a retract. Okay, so this is a retract. So in other words, if you look at the condition of the retract, so it says that when you apply I first and you realize, so I'm using the word realize to say that this A is included in X, but as we have seen in our example of R1 contained in R2, that this inclusion might not be exactly the identity. Okay, so that's why we are using this map I. Okay, so we have this map I from A to X, and this A is a retract of X if there exists R from X to A such that this composition is identity. So in other words, you start from A and you ended up at A, and this map is basically the identity of A. Okay, so so can we say from here that R when restricted to A will be the identity of A? Okay, so let's see if we can derive from this definition that R. Okay, so this is a retract. Okay, so we are trying to see how this R behaves when restricted to the subspace A of X. Okay, so of course R is a map from X to A, and now we are going to see when R restricted to A, what will be the behavior of this thing. Okay, so we can see from this expression. Okay, so first we apply I on the elements of A, so basically we are realizing A as elements of X, and then we apply R on these elements and we are getting the identity of A. So in other words, when we apply R on the elements of A, then it behaves like the identity. Okay, so we can say that when we apply R on the elements of X, then we get this map and we will get exactly A. Okay, so R of X is equal to A. Okay, so we are not losing any other element because this R when restricted to A is the identity of A, so we will get each and every element of A in the image. Okay, so that's how R will behave, and now let's see what is this condition. Now this condition says that when I apply R and then I apply identity, so in other words, so this identity is there just to make sure that we are realizing the elements of A as elements of X. So A is embedded inside X. Okay, so basically this is a map which is taking the elements of X to the elements of A, and this identity takes elements of X to the elements of X. Now this homotopic relation says that this map taking X to A is homotopic to the map identity which is taking elements of X to the elements of X. Okay, so in other words, we can say that this X is image of the map identity, and this A is the image of the map I composition R, and they are homotopic. So in other words, we can say that if I start at t is equal to 0, then I will have the whole X, and when I move on and reach t is equal to 1, then I will be squeezed to this subspace A of X. Okay, so continuously I can deform this whole space to this subspace of X. Okay, so that's what it means by deformation retract. So we can say that we have a subspace A of X, and we can continuously deform this whole space X to this subspace A of X. So mathematically speaking, how we write it, we say that the identity map which takes elements of X to the elements of X, okay, so this identity map is homotopic to I composition R. So this R is basically a continuous function from X to A, and this I is there just to say that we are going to realize the elements of A as elements of X. Okay, so this map is homotopic to identity of X. Okay, so deformation retract, once again, roughly speaking, we can say that the total space, the whole space is basically continuously deformed to a subspace of the space. Okay, so for example, look at these letters. Okay, so we can say that this is the whole space, and these line structure. Okay, so this line structure inside this alphabet A is basically a subspace of A. Okay, we can define a function from this space A to this space A. Okay, so this will be identity on the elements of this A, and it will take elements of this whole space to these three lines. Okay, so how we define this map? So very simply we can say that take an element and take another element and make a line, and then join these 2 points. So how we define this map is very simple. So take an element in this space and move it to the nearest point at this inside A. Okay, so in using this idea, we can deform each and every point of this A to this A. So in other words, we can say that this A is deformation retract of this whole space A. Okay, similarly the same happens for B and C, and similarly we can define many other examples. So for example, consider a cylinder. Okay, so cylinder has a base. Let's say this is the base circle, and this is cylinder. Okay, so we can say that this base circle is deformation retract of this cylinder. So this cylinder is the total space, and this circle is basically the subspace of this cylinder, and we can define. Okay, so how we define? So for example, if this cylinder is inside 3-dimensional space, so we can define projection. Okay, so let's say this circle is contained in XY plane, and this is the Z axis, so we can define the projection. So in other words, just ignore the Z coordinate, and that function will act like a deformation retract. So that will act like, okay, so R goes from this cylinder C to this circle S, and taking elements of the cylinder to the elements of circle. So projecting or ignoring the Z coordinate, or taking any element and taking its Z coordinate to be 0 will give me elements of this circle. So this act like a deformation retract. Okay, and similarly we can find many other examples of deformation retract. So roughly speaking, a subspace A of a space X is deformation retract if the whole space can be deformed into that subspace. So let's recall a definition of homotopy equivalent. So what is homotopy equivalence? So a map F from X to Y, a space X to space Y, is homotopy equivalence if there exists another continuous map G from Y to X such that this is homotopic to identity. Okay, so why we are looking at this definition? So if you look at the definition of the deformation retract, okay, so the space A is deformation retract of the subspace A of X if there exists continuous function R from X to A, and of course this embedding is continuous such that, okay, so if we So every deformation retract is also a retract. So applying the definition or the condition of retract, we get the following, that if we start from A and apply R, then this is equal to identity of A. Okay, so of course if it is equality, then it is homotopy as well. So in other words, we can say that the first condition is satisfied. And secondly, using the definition of deformation retract, so this is homotopic to the identity of X. Okay, so we have the following two conditions, and we can easily see that if a subspace A of X is deformation retract of X, then X and A are homotopy equivalent. Okay, so and then we have the following important result, that if there is a homotopy equivalence between two subspaces, then their homology groups are isomorphic. And the proof of this was very simple. So Hn is a functor, and if F is homotopy equivalence, then there exists a map G from Y to X such that F composition G is homotopic to the identity of Y, and G composition F is homotopic to the identity of X. Okay, so applying Hn on these compositions, so F composition G, so Hn is a functor, so it will respect the composition. Okay, so this is equal to n of G, and this is homotopic. So if two maps are homotopic, then their homologies are equal. So this is equal to the identity. Okay, and similarly when we apply Hn on G composition F, then this is also the identity. Okay, so in other words, we can say that we have identity map from Hn. Okay, so we have this map Hn X to Hn Y, and if F is a map from X to Y, then we have this map Hn F from Hn of X to Hn of Y, and similarly if there is G from Y to X, then we have this Hn of G, this to this, and these are homomorphisms. Okay, so Hn of F and Hn of G are homomorphisms, and they are inverses of each other because their compositions, they are both compositions are identity. So we can say that Hn of X, okay, so this whole discussion implies that Hn of X is isomorphic to Hn of Y. So a very simple result. Okay, so in this case we can say that if A, which is a subspace of the whole space X, is if A is a deformation retract of the space X, then their homologies are same. Okay, so that's the result. If A is deformation retract of X, then Hn of A is isomorphic to Hn of X. So their homologies are isomorphic for each and every n greater than or equal to 0. Okay, so let's recall another thing from our previous lecture, reduced homology. So in reduced homology, we define each and everything similar to the homology except for one thing, where we change this portion of the chain complex, and we define another map epsilon, which is taking elements of these zero chains to the integers in the following way. Okay, so in other words, we can say that the only change will be in H naught tilde, and rest of the homology groups will be the same. Okay, so using this chain complex, the homology that we define is called the reduced homology. And as I said earlier, that for each and every n, there is no difference between the reduced homology and the homology, and the only difference between H naught of X and H naught tilde of X. Okay, and there is a relation between these two as well, and we have done that, and the relation between them is the following. So the reduced homology of X and the homology of X satisfy this short exact sequence. So in other words, we can say that H naught of X is equal to Z and direct sum with H naught tilde of X. Okay, so in other words, if H naught of X is Z, then H naught tilde of X will be 0. So reduced, we have seen that the homology of a point is z if n is 0, and this is 0 otherwise. Okay, so hi star is 0 otherwise. But if we consider the reduced homology, so due to this relation, the reduced homology for each and every I of point is 0. Okay, so that's a little consequence of this condition, okay, that we impose at the end. And so we have the following expression as well. So we have seen that in fact the homology for any n, the relative homology is not the same as the homology of the quotient, but that the thing which is called reduced homology that we defined is basically satisfy something like this. So in other words, we can say that the homology of the relative homology of x with respect to a is basically the reduced homology of the quotient space. Okay, so which is very important result. And the next thing was the reduced homology is basically Hnx x naught, so the relative homology of x with respect to some point. Okay, so point is also a subspace of x. Okay, so this is the reduced homology. Now we can also observe the following thing. So now we are going to see some other facts about reduced homology. So if we have a subspace A of x, then I have the following short exact sequence of chain complexes. Okay, and from this short exact sequence I have the following long exact sequence, and these are induced by, so this is induced by inclusion, and this is induced by the quotient, and this is the connecting homomorphism. Okay, so now we have the following fact which we are presenting without the proof. So the fact is very simple. So in this short exact sequence, if we define this long exact sequence from this short exact sequence, then this also holds for reduced homology only if we use the reduced homology of A and X, and the relative homology remains the homology and not reduced homology. Okay, so this result is very effective, and we'll be using this result in our coming discussion. Okay, now we have come to our first important tool for calculating the homology of any topological space. So this is called excision. Okay, so what is excision? So if we have a space X, and if I have some subspace A of X, and there is this set A which is there is this set U which is contained in A. So this is set U which is contained in A, such that the closure of A is contained in the interior of A. So what does it mean? So the closure of U is basically the smallest closed set containing U, and the interior of A is the biggest open set contained in A. Okay, so this condition also needs to be satisfied. Then we have the following inclusion. Okay, so X minus U is contained in X, and A minus U is contained in A, induces the following isomorphism. Okay, so the relative homology of X minus U, A minus U is isomorphic to the relative homology of XA. In other words, what we have done is that we can excise, we can cut off a subset U of A, which is also a subset of X. So we can excise it, we can cut this set off if this condition is satisfied that the closure of A is contained in the interior of A. Okay, so if this condition that the closure of U is contained in the interior of A is satisfied, then we can cut off this set U, and the homology, the relative homology, will be isomorphic. Okay, so that's why, so we are cutting off, we are excising this U, and that's why this is called excision. And there is excision 2. So the statement of excision 2 is if we have two subspaces of X, such that this space X is equal to the interior of X1 union the interior of X2, then the inclusion. Okay, so X1 is contained in X1 union X2, and X1 union X2 is contained in X1 intersection X2 is contained in X2, and which is of course equal to X2. Then this induces the following isomorphism. Okay, so X1 intersection X2 to Xn X2. Okay, so we have two excision tools, but the fact is these two tools are equivalent. Okay, so we can use either of the tools, and basically they are equivalent, so it depends on the situation, and we will be getting homology, and we will be getting information about the homology using this tool. Okay, so it depends on the situation, and we will decide which tool is more efficient, but the fact is these two tools are equivalent. Okay, so let's go back and see what is the axiomatic definition of homology. So in this axiomatic definition of homology, there was this excision axiom as well. Okay, so we can say that the singular homology satisfy this excision axiom as well. Okay, so we are not proving the excision axiom for the singular homology, but we will be using it, and we will be using it to calculate the homology of spaces. Okay, so but singular homology satisfy the excision axioms, which is one of the axioms of the homology. So let's see how to apply excision to calculate the homology of sphere. So when n is equal to 0, we have 2 points on the real line. So in other words, we have two connected components, so this implies that H naught of S naught is equal to 2 copies of Z, because there are two path connected components. Okay, so when n is greater than 0, then the sphere, for example circle, sphere, two sphere and higher dimensional spheres are path connected, so Sn is path connected. So if they are path connected, then we can say that the zeroth homology of Sn is basically Z. Now let's see how to show these homologies. Okay, so to show these homologies, we have 3 steps to calculate. Okay, so in the first step, we consider dn and an. So what is dn and what is an? So dn is the disk, we know that, and an is basically annulus inside this dn. So how we define this thing? So x belongs to dn such that the distance of the points of dn is basically less than or equal to 1 and greater than or equal to 1/2. Okay, so for example, if we take n is equal to 2, then n is equal to 2 is basically a disk inside R2. So it is this disk, and this A2 will be this portion. Okay, so this portion, this green shaded portion, is basically A2. Okay, so basically it is annulus inside this disk. Okay, so let's calculate the relative homology, and let's see what will happen. Now calculating relative homology, consider this sequence hi an goes to hi dn goes to hi dn an goes to hi minus 1, okay, an up to so on hi minus 1 dn hi minus 1 dn an up to so on. Now we have also seen that this sequence is true if I replace the homology of the spaces an and dn with this reduced homologies. And also we know that homology of the disk is 0 because the disk is contractible to a point, so that's why we can say that these things are 0. And so this implies that hi dn an is isomorphic to, because if these two spaces are 0, then these two spaces are isomorphic, so isomorphic to I minus 1 tilde an. Okay. Now if hi dn an is isomorphic to hi minus 1 an, and this is the reduced homology, then let's see what is the space an. So once again consider the case of two-dimensional space. So in this two-dimensional space we have this annulus as a2, and now we can see that this annulus can be written as, so now this an is equal to Sn minus 1 cross I. Okay, so we can say that this is basically homeomorphic to this circle, and taking cross with I, and we will write down these circles and we will get this annulus. Okay, so also this annulus has this inside circle as deformation retract. Okay, so we can say that this inside circle is deformation retract of this annulus. So also Sn minus 1 is a deformation retract of an. Okay, so of course this implies that the homology I minus 1, the reduced homology of Sn minus 1 is the same as the reduced homology of an. Okay, so that's step number 1. So let's consider step number 2. So in step number 2 we consider Sn, and we consider a subset un of Sn, which is basically set of all points of the sphere such that xn plus 1 is less than 0 and is greater than or equal to minus 1. Now let's once again consider the case of two-dimensional and consider this sphere in three-dimensional space. This u2 will be this lower hemisphere, but the points on xy plane are not included because there is this strict inequality. Okay, so why is this lower hemisphere? So if I take the coordinates of R3 to be x1, x2, x3, and this x3 is the z coordinate, and then basically we are assuming, we are imposing that x3 is less than 0 and greater than or equal to minus 1. So of course there is no point of the sphere below minus 1, so it is basically set of all points below, strictly below xy plane and above this point, this southern hemisphere, southern pole of this sphere. Okay, so these are the points. This is u2. Now define another set Bn. So this Bn is equal to x belongs to Sn such that xn plus 1 is less than or equal to 1 by 2 and greater than or equal to minus 1. Okay, so once again consider the case of S2. So in this case of S2, this B2 will be this region. So set of all points such that the z coordinate is less than or equal to 1 by 2. So z is equal to 1 by 2 is this plane, so we are taking this to be xy plane. So the intersection of this sphere with this z is equal to 1 by 2 plane is this circle, and every point of the sphere which lies between this plane and plane z is equal to minus 1. So in other words, it's this whole region. Okay, so this is basically our B2 in the case of S2. And so these are the two sets. Now remember that if we want to apply excision, then we should have this condition, which is basically satisfied in this case, that the closure of un. So in this case the closure of u2 will be everything below xy plane, and also the circle on xy plane. Now the circle is included in the closure of U2 in this case. Okay, so this is contained in the interior of Bn. Of course, in this case it is contained in the interior, and the similar situation will happen in higher dimensional cases. Okay, so this condition is satisfied. So by Excision 1 we can say that Hi Sn minus Un, so we can excise this set Un, and we have this Hi Sn minus 1 Un. So after excising this Un from Sn and Bn, we have this following thing, that this must be isomorphic to Hi Sn Bn. Now this Sn minus Un, so if I take this Un from this Sn, so once again considering the case of two-dimensional case, so I have this upper hemisphere, and if we take out this U, so when we take out this U, then the circle on the xy plane will still be included, and because this is strictly less than 0, so we can define a map from the points of this S2 to this disk in R2. Okay, so this will be homeomorphism, and same is the case in higher dimensional cases. So we can say that Sn minus Un is homeomorphic to Dn. Okay, and similarly Bn minus Un, so if you once again observe this case, if we take out this green shaded area from this B2, then I will have a strip on this sphere. So this strip is basically is the same as this A2. So in general the same situation will happen, and this Bn minus Un will be homeomorphic to An. Okay, so using these two homeomorphisms and this isomorphism, we can say that Hi Sn minus Un Bn minus Un is isomorphic to Hi Dn An, and using this isomorphism we can say that Hi Sn Bn is isomorphic to Hi Dn An. Okay, now also from here we can say that this is isomorphic to the reduced homology of, okay, so this is isomorphic to this, so we can say that reduced homology Hi minus 1 of Sn minus 1. Okay, so far we have proved this thing after two steps. Sn Bn is isomorphic to Hi minus 1, the reduced homology of Sn minus 1. Okay, so let's go to step number 3. So let's see how we have what we have proved so far. So Hi Sn Bn is isomorphic to the reduced homology I minus 1 of Sn minus 1. Now let's explore this homology, this relative homology further. So for that consider this long exact sequence. Okay, so Bn goes to Hi Sn goes to Hi Sn Bn goes to Hi minus 1, Bn goes to Hi minus 1, Sn goes to Hi minus 1, Sn Bn, up to so on. Okay, so this Bn is basically contractible to a point. Okay, so that's why we can say that this Bn is 0 and this is 0. So in other words we can say that this Hi Sn Bn is isomorphic to Hi Sn. Okay, so the reasons are very simple, because this is an exact sequence, so the image of this must be equal to the kernel of this, so the image of this is 0, so the kernel of this is 0, so that's why this is 1 to 1, and similarly the image of this is equal to the kernel of this, and the kernel of this is the whole space, so that's why this is onto, and this is a homomorphism as well, so 1 to 1 and onto, so that's why isomorphism. And from this result we can say that this is isomorphic to hi minus 1 of Sn minus 1, so the reduced homology. And similarly, using the properties of reduced homology, we can say that I can replace these H's with the reduced homology, and the same short exact same long exact sequence holds, and so we have the following result. Okay, so now we can say that hi reduced homology of Sn is isomorphic to hi minus 1, the reduced homology of Sn minus 1, isomorphic to Hn I minus 2 of reduced homology of Sn minus 2, up to so on, and at the end we will get the following. Okay, so hi minus n, okay, so reduced homology 0, okay, so n minus n is 0. Okay, so using this we can say the following thing: if I is equal to n, so if I is equal to n, then this is the H naught reduced homology of S naught. Okay, and we also know the relation between the reduced homology and the homology, and the relation is the reduced homology of space X goes to homology of X goes to Z. So we have this short exact sequence, and this implies that the reduced homology and the homology are basically related in the following way. Okay, so plus Z. Okay, so S naught, so what is the reduced homology of S naught? So the homology of S naught is Z plus Z, so we can say that the reduced homology of S naught is Z. Okay, so now this is isomorphic to Z, and so we can say that when I is equal to n, then this reduced homology of Sn is isomorphic to Z, but when I is greater than 0, then the reduced homology and the homologies are the same, so that's why this is isomorphic to Hn Sn. Okay, so that's the first result. And when I is not equal to n, we know that when I is not equal to n, and for example in this case when I is greater than n, so that this is greater than 0, okay, so that this number is greater than 0, then this S naught is 0, and so whenever I is not equal to n and I is greater and this number is basically greater than 0, then this number is 0, and so the rest of the things are 0. So whenever I is not equal to n, then Hi of Sn is equal to 0. So let's see if that's what we wanted to prove. Okay, so when I is not equal to n, then we have 0. When I is equal to n, we have Z, and that's what we wanted to show. Now let's go to another tool for calculating homology. So we have this Meyer-Vittori's theorem. So this theorem is another tool for calculating the homologies, and this MV sequence can be derived from the Eilenberg-Steenrod axioms. Okay, so let's see what is this MV sequence. So if we have two subspaces of space X such that the space X is equal to the interior of X1 union the interior of X2, then there is this exact sequence. Okay, so this map I1 is basically the inclusion of X1 intersection X2 inside X1, because if we have let's say this is X1, this is X2, then this X1 intersection X2 is contained in X1 as well as in X2. So I1 is the inclusion of X1 intersection X2 into X1, and I2 is the inclusion of X1 intersection X2 into X2. Okay, so if we have an inclusion, okay, so in other words we have a continuous map, then we can say that there exist maps between the homologies. Okay, so in other words we can say that there will be a map, so corresponding to this I1, there will be a map I1 star from the homology of x1 intersection x2 to the homology of x1. Okay, similarly, if there is inclusion I2 star I2, then there will be a map I2 star from hn x1 intersection x2 to hn x2. Okay, so we have the following two maps. Now I can take these two maps and define this map. So first apply I1 star on these elements and get the elements of hn x1, and then apply I2 star on this and get the elements of hn x2 and take their direct sum. Okay, and similarly I can apply the following map G star and J star. So what is G star? So G is basically the inclusion of x1 into x, and J is the inclusion of x2 into x. Okay, so these x1 and x2 are included in x, so that's why so using these inclusions we can also define J star and low star. So in other words, we have J low star G star from hn x1 to hn x, and J star will be mapped from hn x2 to hn x. Okay, so apply G star on the elements of hn x1 and apply J star on the elements of hn x2, and when we apply these elements on these two elements, then we get the elements of xn. Okay, and then from hnx to hn minus 1 x1 intersection x2, we have this connecting homomorphism. So what is this connecting homomorphism? So this is equal to q star, h inverse star, and d. Okay, so if we have this q, then we will have this q star, and we have this h, so we will have h star and then h star inverse, and then we apply d. Okay, so D is basically the connecting homomorphism of this coming from this sequence. Okay, so this sequence will define a sequence between the homologies of x1 intersection x2, x1 and x1 intersection x2. So from that sequence we will have a connecting homomorphism. So D is that connecting homomorphism. Okay, so from these three we can define these connecting homomorphism, capital D. Okay, so define in this way. So that's what this MV sequence is. So let's go on and try to calculate the homology of a torus using this sequence. Okay, so we know that the homology of a torus when I is equal to 0 is Z, because it is path connected, so there is nothing to prove. So H naught of T2 is Z. Okay, so when I is equal to 1, then we have Z plus Z, and we will see why this is true. And when I is equal to 2, then this is Z, and we will also see. So roughly speaking, if we want to interpret the homology, then basically this says that there is only one two-dimensional hole, and we know that if we have this hollow torus, then what is that two-dimensional hole? So the inside of the torus is the two-dimensional hole. Okay, and when I is equal to 1, then we have two types of one-dimensional holes, so for this circle and this circle. Okay, so these are the one-dimensional holes in the torus, and that's why we have Z plus Z. So that's a rough interpretation of the homology of the torus. So let's see how to calculate homology of a torus using the MV sequence. Okay, so we define the following two subsets of the torus, A and B, and this shaded area is their intersection. Okay, now this A is basically homeomorphic to a cylinder. Okay, and we have also seen that a cylinder is has a circle as deformation retract. Okay, so cylinder has okay, so let's consider this cylinder. Okay, so this cylinder has the base of the cylinder as the deformation retract of the cylinder. So we can say that this set A has basically circle as deformation retract. Okay, so A has circle as deformation retract. Okay, so this A is homeomorphic to a cylinder, and cylinder has circle as deformation retract. So so topologically speaking, A is the same as circle. So that's why we can say that the homology of A and the circle are same. So what about the homology? So Hi of A. So the homology of the circle, we know that this is Z. If I is equal to 0 and 1, this is 0 otherwise. Similarly, B is also deformation retract, has circle as deformation retract, because B is the same as cylinder and cylinder has a circle as deformation retract. So we can say that we know the homologies of A and B. Okay, now let's apply MV sequence to calculate the homology of the torus. So Hi A intersection B goes to Hi A direct sum, Hi B goes to Hi the torus T, and this goes to Hi minus 1 A intersection B, and this goes to Hi minus 1 A direct sum Hi minus 1 B up to so on. Okay, so we know the homologies of HIA and HIB, so basically we know these things. Okay, now let's concentrate on A intersection B. So what about A intersection B? So A intersection B are basically these two circular strips. So in other words, we can say that A intersection B behaves, okay, so A intersection B behaves like two circles, because this is a cylinder and cylinder has the base circle as deformation retract. Once again, this is a cylinder and cylinder has circle as deformation retract. Okay, so we have two cylinders, or we can say that we have two path connected components. Okay, so we can say that H naught of A intersection B is basically equal to Z plus Z, and similarly H1 of A intersection B is equal to Z plus Z. Okay, so once again we can use the tricks or the simple tricks of homology to calculate this group. So if you're not convinced, or otherwise we can see that roughly speaking there are two one-dimensional holes. Okay, so one is this circle and the other is this circle, so that's why it is Z plus Z. So if you are not convinced, then I'm leaving this as an exercise for you. Okay, so we have these homologies, and of course it is one dimension, so of course this is circle plus circle, so all the higher homologies will be 0. Okay, so A intersection B is 0 up to so on. Okay, so we know all the homologies except for the homology of the torus. So our next goal is to calculate the homology of the torus using all these homologies and the MV sequence. Okay, so first concentrate on H2 of T. So H2 of T can be calculated in the following way. So H2 of T goes to H1 of A intersection B goes to H1 of A plus H1 of B, and this goes to H1 of T. Okay, now this map is defined as I1 lower star and I2 lower star. Okay, so where I is basically embedding of A intersection B into A, and I2 is basically embedding of A intersection B inside B. Because using these two maps we can define these I lower star, I1 lower star, I2 lower star, and we have this map. Okay, now H1 A intersection B, we know that H1 A intersection B is basically Z plus Z. Okay, so we can take its generators to be, we can say that is z plus z. Okay, so z plus z is generated by 1 0 and 0 1. Okay, so because this is a Z module, so we can say that as a Z module, these two are the generators of the Z module. Okay, so let's concentrate on the map I1 lower star. So it will take these two elements and it will take it to the same element, because we know that H1 of A. Okay, so A behaves like a circle, so also H1 of A is equal to Z. Okay, so it will take this element and it will take to this generator of Z, so we can say it to be 1. Okay, so we can say that I1 lower star will take any of the elements, okay, 1 0 or 0 1. So let's concentrate on 1 0, so this will equal to 1, but this 1 is one of this copy of Z. Okay, so and similarly I2 star of 1 0 is equal to 1, and now in this case I'm taking this 1. Okay, so I'm taking this 1 as the generator of this H1 of B. Okay, so we can say that I lower star 1, I2 star, when applied on the element 1 0, it will give me, so when you apply I1 star and I2 star on this, then we will get 1 1. Okay, so similarly when we apply I1 star I2 star on 0 1, then we get 1 1. Okay, so the matrix of this map, okay, so the matrix of this map becomes 1 1 1 1, and now the problem is to find the kernel of this map. Okay, so because there is 0 on this side, so the image of this is equal to kernel of this, so that's why this is 1 to 1, and so the image of this is equal to kernel of this, so we are interested in finding the kernel of this. So what kind of elements, okay, so what kind of elements of H1 A intersection B, which is basically 2 copies of Z, so let's take A B, goes to okay, so the kernel of this. Okay, so this is basically equal to A plus B, so this is equal to 0, implies A is equal to minus B or B is equal to minus A. So in other words, when we take B is equal to minus A, then in this Z plus Z, this is just one copy of Z. Okay, so in other words, we can say that the kernel of I1 star and I2 star is equal to Z. Okay, so the image of this is equal to kernel of this, so that's why we can say that H2 of T is isomorphic to Z. Okay, so similarly we can consider these maps, and we can try to calculate H1 of T. So what should be the idea? So the idea is very simple, that we want to calculate, okay, so the image of this is equal to kernel of this. Okay, so in the next stage we will have H0 of A intersection B, and which will go to H0 of A, direct sum H0 of B, okay, up to so on. Okay, so now we want to calculate this thing, and we just need to concentrate on these maps. Okay, and of course we also need to know we also need to understand the contribution of this map. Okay, so H1 of T is isomorphic to Z plus Z, so it can also be calculated using this sequence, but I am leaving this as an exercise for you. Okay, so let's go to further applications of the homologies. Okay, so Sn is not a retract of Dn plus 1. So once again, if we want to look at the situation in for example two-dimensional case. So D2, okay, so we have this D2 and this is S1 is the circle which is the boundary, and we want to show that this S1 is not retract of D2. Okay, so if Sn is retract of Dn plus 1, then we should have the following diagram: Dn plus 1. Okay, so Sn, the identity map, identity of Sn, and we should have, so this is the inclusion, and we should have this R such that this diagram commute. Okay, so now this implies that we have the following diagram: Hi Dn plus 1, sorry, in this way, so S Hi of Sn, and it goes identity. Okay, so Hn Hi of identity of Sn, and Hi of Sn, and the image of Hi of this I. So this I is different from this I, so let's say this is I prime. Okay, so Hi of R. Okay, so that this diagram commute. Now we know that this disk is contractible, so this is equal to 0, and we know that when I is equal to n, then this is equal to z. Okay, so in other words, we are saying that this identity map is 0 for I is equal to n. So I is equal to n gives us a contradiction. So if this is true, that Sn is retract of Dn plus 1, then we have this diagram, and this is always 0, and for I is equal to n, we will have this z, and this is the identity map, because the functor Hi takes identity to the identity, so this should be identity map. So this is identity, and since this diagram should commute, so that's why we have this 0 map, because it goes to 0 and it will take, this is homomorphism, so that's why it will take 0 to 0. Okay, so this is 0 map, and this is identity map, which is a contradiction, so we can say that Sn is not a retract of Dn plus 1. Now we have this important theorem from fixed point theory, which is called Brouwer fixed point theorem, and it says that if we have a function from the disk Dn to Dn and it is continuous, then there must exist x belongs to Dn such that f of x is equal to x. So this x is called the fixed point of this continuous function. So the case n is equal to 1 has very simple proof, which is basically using simple ideas of topology, but when we are going to the higher dimensions, then the result is very non-trivial. But using homology we can prove this result. So let's see how to prove this result. So once again, consider this two-dimensional case of D2. So if we have a point x, and since it's a function from Dn to Dn, then there will be f of x, which will also be contained in the disk. Now we can define the following map. So taking this x, f of x, and taking to the nearest point of the circle. Okay, so or the n minus 1 sphere. Okay, in this generalized case, so we can define this map. Okay, so we can do it as long as x is not equal to f of x. Whenever x is equal to f of x, then we can't define this map. Okay, so consider the following image, and if for each and every x, if we can have this map such that or we can say that if for each and every x and f of x are different, then we can define this map. And if we can define this map, then so if we can define a map from Dn to Sn minus 1 for each x belongs to Dn, then this implies that Sn minus 1 is a retract of Dn, which is a contradiction. So that's why there exists at least one x belongs to Dn such that f of x is equal to x. So using the idea of homology, we have this simple proof of the Brouwer fixed point theorem. Now if m is not equal to n, then Rm and Rn are not homeomorphic. So if they are homeomorphic, so if Rm and Rn are homeomorphic, and remember that m is not equal to n, then Rm minus 1 point, let's say x naught, must be homeomorphic to Rn minus the image of this 1 point. Okay, let's call it f of x naught. Okay, if they are homeomorphic, then there exists an homeomorphism, and we are calling that homeomorphism to be f from Rn to Rn, and so if this happens, then these must also be homeomorphic. Now what about the homology of this Rm minus x naught and the homology? So there must be isomorphic as well. So Rn minus f of x naught. Now the point is, if I have R2, then if I take this 1 point out, then it behaves like S1. Okay, so it's a circle. So it's basically, okay, so it behaves like an n minus 1 sphere and behaves like n minus 1 sphere. So these are spheres, and we know that from the previous result, if m is not equal to n, then these spheres are not homeomorphic, and using this result we can say that Rm and Rn are not homeomorphic. Okay, so if n is greater than or equal to 0, then Sn is not contractible, because if it is contractible, then it has the same homology as the homology of a point, and we know the homology of a point, hi of star, this is equal to z if I is equal to 0, and this is equal to 0 if I is not equal to, okay, so otherwise. Okay, and we know the homology of sphere, so hi of Sn, so this is equal to z if I is equal to n, and this is 0 otherwise. So we can see that their homologies are different, so that's why we can say that Sn is not contractible. So once again, if we want to prove this result using other tools of topology other than homology, then it is very complicated to prove this result. Okay, but we have seen that we can show this just writing down the homologies of point and the n sphere, and the result is proved. So that's the end of today's lecture. In today's lecture, we have seen two other tools for calculating the homology, excision and MV sequence, and we apply these tools to calculate homologies, and in particular we have seen that the homology of torus is very simple to calculate using these tools. Next time we will continue with the applications of the homology, and we will see that how we can apply these tools to calculate the homologies of other objects which are otherwise very non-trivial. This is the end of the lecture. Thank you very much, and Allah Hafiz.